Hello, and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry, and today I'm going to run through a few undergraduate level physics questions. So here we have our first question. So it's at what distance along the central axis of a uniformly charged plastic disc. So we have a disc, and it's asking, nope, let's try to draw straight lines. What distance, I don't know if that was much better. So what distance, and I'm going to call it R, along the central axis of the disc, which has a radius R equal 1.28 meters, is the E field 1/6 the magnitude of the field at the very center of the disk. So that would be, so we're wondering, where is ER equal to 1/6 E0? So first we need to figure out what ER is, and then we can solve for E0 and figure out exactly what R we're looking for. Okay, so we've got a uniformly charged plastic disc, which means that the total charge on the disc, which I'm going to call big Q, is our charge density times our area. For a disc, it's going to be pi r squared. And we can kind of play the same game here as we would as for moment of inertia. So we can define a small area at some radius r prime, and it would have some width dr prime. And so it would have some incremental charge of 2 pi r prime rho dr prime, where rho is our charge density. And so we can use this in our electric field expression. Now, electric field is a vector quantity, so it's a little bit trickier than with moment of inertia. So it'd be, I'm going to use double primes here just again to differentiate. And so it's dq, and it's in the direction of r hat prime. So if we're looking for our directionality here, it's going to be, so we've got some disk and some incremental area and some and so the r hat prime here, or the r double prime here, is this, and what we're looking to solve for is this r here. So if we look at the triangle we've just drawn, right, here is our r double prime, here's the r we're interested in, and then here is our r prime, which we've defined in terms of our charge density there. And so we can readily see here that our double prime is the square root of r prime squared plus r squared. So that's from Pythagoras. Okay, so that's that. We can deconvolve our double primes. So now the vector quantity here. So if we're looking for just the radial component, then our r hat double prime is going to equal so our r double prime vector over our magnitude. So we know that, and we know that we're going to have to integrate this expression. So we can kind of see that although our electric field is going to add up in the r direction, it's going to cancel in the other directions, right? So there's an equal if we draw two r double primes here, we can see we have an equal and opposite directionality here, and so it's actually going to cancel in the other directions. But we can write this as r over r double prime, where r is a regular r vector length, and that would be in the r hat direction, and plus. And we could just call this, let's just call it r phi. So I don't really know what the length is there, but I know it's going to cancel. So phi being the angular direction. But I can see that if I just want my r direction, then it's going to be, we just need this piece here. So putting this all together, sorry, I missed a square there. And so this would be r prime squared plus r squared, and then multiplied by an r over r double prime. Which I should have just kept in there in retrospect. So r double prime squared, or RER is r over 4 pi epsilon naught dq over r double prime cubed. Now, subbing in our values that we rationalize through here, this becomes, and dq was set up as 2 pi r prime dr prime times our charge density, and our r double prime we just said was r prime squared plus r squared. And so this will be to the 3/2. And so then there is our electric field expression that we're going to start with. And then we just need to integrate this. So now ER is bringing out everything that's not in terms of R prime. So we've got these. We're going to integrate from 0 to r prime dr prime over r prime squared plus r squared to the 3/2. So the best way to do this here is a substitution. So if we say that u is r prime squared, then r prime, then du is 2 r prime dr prime. So then r rho over So then ER is R rho over 2 E naught. We can see that we need a 2 up here, so this is going to give us a half integral. Our limits now are going to be 0, putting in the values into R prime to R squared, and then du over u plus R squared to the 3/2. Now we can solve this pretty readily. All right, so if we consider u plus R prime squared to the minus 1/2, we know that when we integrate, basically this guy is going to just drop down by 1 factor. So if we take the derivative of this, then we get minus 1/2 u plus R squared to the minus 3/2. So the integral of this is just going to be minus this guy. Okay, so then ER is R rho, and maybe you can get our half factor in here too, over 2 E naught times minus u plus R prime squared to the minus 1/2 from 0 to R squared. Okay. So then working this through, we've got R rho over 2 E naught, and minus 1 over R squared plus R prime squared. Oh, oops. At what point did that become R prime squared? My apologies. So right there, I guess? Is that? Yeah. It's just right there. Anyway. So I'm just going to erase these primes, so that should just be R squared. Minus a minus 1 over, putting 0 in for u, just gives, and this should be to the power of 1/2 over R squared to the power of 1/2, which is just R, and then the minuses here will cancel. So R rho over 2 E naught, 1 over R minus 1 over square root of R squared plus R squared. And then we could pull the 1 over R out here to give us rho over 2 E naught, 1 minus R over root R squared plus R squared. Okay. So then there's our E field expression. So now the question is, at what point is ER equal to 1/6 of E0? E0 is rho over 2 E naught, 1 minus 0. So that whole thing goes to 0. And so it's just rho over 2 E naught. So then we're looking for where our ER, so that's rho over 2 E naught, 1 minus R over root R squared plus R squared is equal to rho over 2 E naught. So obviously we can cancel both sides here. Oh, sorry, is equal to 1/6 rho over 2 E naught. So then we're looking for where 1 minus R over root R squared plus R squared is equal to a sixth, or rearranging, so we've got r over root r squared plus r squared is equal to 5/6, or r equals 5/6 root r squared plus r squared, squaring both sides. And now rearranging for our r squared. So then we get r squared 11 over 36 equals 25 over 36 r squared, or r equals 5 over root 11, so rearranging here, r. Now we're given in the question that r is 1.28 meters, so we can solve this numerically for 1.93 meters. Okay, so then there's our r. Okay, so checking the solution here. So there's our E field where they use sigma for their charge density, but that's okay, doesn't really matter. So plugging in, rearranging, solving, and then we get 1.93 meters. So that looks good.